A multiplexer, MUX, is like a railway switch that lets one of many tracks, data lines, be chosen and sent to a single destination. The symbol is a rectangle with multiple data inputs, D0 to Dn-1, a set of selection lines S0 to Sm-1, where m equals log base 2n and one output y. The demultiplexer, DEMUX, works the opposite way. It is a single track feeder that branches out to many tracks, routing the incoming data to exactly one of several outputs. Its symbol shows one data input, the same number of selection lines, and many outputs, y0 to yn-1. In both devices, the selection lines act like a binary address that tells the circuit which path to open. The fundamental operation is purely combinational. The output is a logical function of the data inputs and the address bits, with no memory or clock needed. Explanation. For an n-to-1 multiplexer, the truth table lists every possible combination of the m equals log base 2 of n select bits and shows which data input appears at the output. Example for a 4-to-1 multiplexer, n equals 4, m equals 2. When S1 is 0 and S0 is 0, y is D0. When S1 is 0 and S0 is 1, y is D1. When S1 is 1 and S0 is 0, y is D2. When S1 is 1 and S0 is 1, y is D3. The Boolean expression derived from the table is y equals not S1 and not S0 and D0, or not S1 and S0 and D1 or S1, and not S0 and D2 or S1 and S0 and D3. Similarly, a 1-to-n demultiplexer with one data input D and M select lines produces n outputs where only one carries the data and the rest are 0. For a 1-to-4 demultiplexer, y0 equals not S1 and not S0 and dy1 equals not S1 and S0 and dy2 equals S1 and not S0 and dy3 equals S1 and S0 and d. These equations are often written using sum of products form. They illustrate that each output is a logical AND of the data line and the unique combination of select bits. The Boolean algebra shows that a multiplexer can implement any Boolean function of up to m variables by connecting the function's minterms to the data inputs and using the select lines as the variables. A MUX or DEMUX can be built from only NAND, NOR, and NOT gates because these gates are functionally complete. For a 2-to-1 MUX, the sum of products expression y equals not S and D0 plus S and D1 can be implemented as invert S with a NOT or NAND with tied inputs, and the terms using NAND gates followed by another NAND to act as an OR De Morgan. Specifically, NAND 1 equals NAND of not S and D0, which produces NOT of not S and D0. NAND 2 equals NAND of S and D1, which produces NOT of S and D1. Y equals NAND of NAND 1 and NAND 2, which gives NOT of open bracket NOT of not S and D0 and NOT of S and D1 close bracket, which simplifies to not S and D0 plus S and D1. The same idea works for a DEMUX. Each output y sub I equals D and the select pattern. Using NAND gates, we first generate the required select pattern, for example not S and S0 with NAND or NOT, then NAND it with D and finally invert if needed. Because NAND and NOR are interchangeable, a designer may choose the one that gives the smallest gate count or best timing for a given technology. Large multiplexers are usually constructed by connecting smaller ones in a tree-like hierarchy, much like building a large highway interchange from several simpler overpasses. An 8-to-1 MUX can be made from 3 2-to-1 MUX stages, or from 2 4-to-1 MUZs followed by a final 2-to-1 selector. Method 1 Binary tree of 2-to-1. Level 1 for 2-to-1 MUZs select between pairs of the 8 inputs, producing 4 intermediate signals. Level 2 2-to-1 MUZs choose between the 4 intermediate signals, yielding 2 signals. Level 3 2-to-1 MUX selects the final output. The total number of select lines is 3, where S2 selects the top-level branch, S1 the mid-level, and S0 the bottom level. Method 2 4-to-1 plus 2-to-1. 2 4-to-1 MUZs each handle 4 inputs, controlled by the 2 least significant select bits, S0, S1. Their outputs feed a final 2-to-1 MUX, which is controlled by the most significant select bit S2. The same hierarchy works for DEMUX. A 1 to 8 DEMUX can be built from 1 to 2 DEMUX feeding 2 to 4 DEMUS, or from 3 to 2 stages in a binary tree. Hierarchical design reduces wiring complexity and allows reuse of verified small unit blocks. Propagation delay (TP) is the time a change at any input takes to affect the output. For a MUX built from NAND gates, TP is roughly the sum of the delays through each gate level. For example, 3 times TP of NAND for the 2 to 1 implementation. Setup time, T setup, and hold time, T hold, matter when the MUX is part of a sequential system driven by a clock. The select lines must be stable for a short window before and after the clock edge to guarantee correct routing. Fan-out refers to how many gate inputs a single output can drive without excessive delay. In a large MUX, the intermediate nodes may fan out to several next stage MUXes. Excessive fan-out increases the effective delay because each gate's input capacitance slows the driving node. Designers mitigate this by buffering, adding a small inverter or a dedicated buffer, or by limiting the number of branches per node. Timing analysis typically calculates the worst-case path, the longest chain of gates from any data input through the select logic to the output. For an 8 to 1 MUX built as 2 4 to 1 stages, the worst-case delay equals delay of 4 to 1 plus delay of 2 to 1. Tools such as static timing analysis, STA, use these models to verify that the MUX meets the required clock period. Explanation: the duality principle states that switching the roles of and/or and 0/1 in a Boolean expression yields a valid dual expression. In hardware, a MUX and a DEMUX are duals. If you interchange data inputs with outputs and keep the select lines the same, the circuit functions as the opposite device. Conversion technique: to turn a 4 to 1 MUX into a 1 to 4 DEMUX, simply feed the single data line into all data inputs of the MUX and treat the original data inputs as enable signals for each output. Conversely, a 1 to 4 DEMUX can act as a 4 to 1 MUX by wiring the 4 data inputs to the enable pins of the DEMUX and using the select lines to choose which enable is active. The DEMUX single output then carries the chosen data. Practical designers often use a combined MUX-DEMUX block, sometimes called a switch, that can be configured in either direction by a mode control bit. This is common in FPG, a routing resources where a configurable switch can route a signal to one of several destinations or select one of many sources. Multiplexers are the backbone of data routing inside CPUs, communication buses, and digital signal processors. For example, a processor's instruction fetch unit uses a MUX to choose between the program counter, a branch target, or a jump address. In function generation, a MUX can directly implement any Boolean function of up to m variables by connecting the function's truth table minterms to the data inputs. This is called a lookup table implementation and is widely used in programmable logic devices, PLDS and FPGAs. Memory address decoding often uses DEMUXes, or decoders, which are essentially 1 to 2 to the n power DEMUXes. When a processor accesses a memory location, the high-order address bits are fed to a decoder that activates exactly one word line in a RAM array, ensuring that only the selected cell is read or written. Other applications include video multiplexing, choosing one video stream among many, audio channel selection, and peripheral selection in microcontroller I/O. For example, choosing which sensor input is connected to an ADC. Explain 1. Design problem. Draw an 8 to 1 multiplexer using only 2 to 1 multiplexer blocks. Show the select line assignments and count the total number of NAND gates needed if each 2 to 1 multiplexer is implemented with 3 NAND gates. Solution hint: use 3 hierarchical levels as described earlier. Total NAND gates equals 8 times 3 equals 24. 2. Truth table derivation. Write the sum of products expression for a 1 to 4 demultiplexer and simplify it using Boolean algebra. Verify that the simplified form uses only 2 NAND gates per output. Solution hint: start from y sub I equals d and not s1 and not s0, etc. Apply De Morgan to obtain NAND form. 3. Delay calculation. An 8 to 1 multiplexer is built from 2 4 to 1 multiplexer stages. Each 4 to 1 multiplexer has a propagation delay of 2 nanoseconds, and the final 2 to 1 stage adds 1 nanosecond. What is the worst-case delay from any data input to the output? Answer: 2 nanoseconds for the first stage plus 2 nanoseconds for the second stage plus 1 nanosecond equals 5 nanoseconds. 4. Setup hold check. In a synchronous system with a 10 nanosecond clock period, the select lines of a 4-to-1 multiplexer have a setup time of 0.5 nanoseconds and a hold time of 0.2 nanoseconds. If the clock-to-cue delay of the register driving the selects is 3 nanoseconds, does the timing meet the requirement? Answer: yes, because the selects become valid 3 nanoseconds after the clock edge, well before the required 0.5 nanoseconds setup time prior to the next edge, and they remain stable for 0.2 nanoseconds after the edge. These sample questions illustrate how examiners expect students to translate theoretical concepts, truth tables, Boolean simplification, into practical hardware designs and timing analyses.